My name is Goodnews Babade. I'm a grade 11 student from Wheeler High School, and I'm going to present my project mentored by Dr. Shubham in the biomedical and sciences category. And today I'm really excited to share with you multimodal deep learning for early equitable cervical cancer detection, which I believe is a solution to addressing a global health crisis through accessible, non-invasive technology. So let's dive right in. According to the World Health Organization 2024 data, every year over 600,000 women face a cervical cancer diagnosis. That's more than the populations of some major cities. For comparison, the estimated number of people in Atlanta, Georgia here is around 500,000 people. So why exactly is this number so high? Traditional screening methods like the pap smear offer 70 to 95% sensitivity. And while these are highly successful in high resource settings, they struggle in regions with limited access to trained cytologists and labs. HPV testing is also another really popular traditional method, and it is highly sensitive, but once again requires expensive equipment and infrastructure that simply isn't available everywhere. And this limited access creates a disproportionate impact where women there have to bear the greatest burden. This crisis inspired my project on how AI could bridge this equity gap. I proposed a novel AI model that didn't just rely on one type of data, but instead integrated three complementary streams of information. My multimodal approach combined pap smear cytology images, molecular biomarkers, and clinical variables such as HPV status and socioeconomic indicators to ensure that these could be used in resource-limited settings. And as the visual shows, it starts with input data, moves through pre-processing and integration, and then outputs a ready data set for analysis. What exactly was my goal with this project? It was to achieve over 95% accuracy while making sure that this could still be used in resource-low settings. So let's move on to the data components. For pap smear cytology image, I used the Harlem dataset, which contains thousands of cell images already classified as normal or abnormal. And then using pre-processing, I resized the images to 224 by 224 pixels for consistency. And this pre-processing ensured the model was able to capture subtle abnormalities. For molecular data, I turned to the Cancer Genome Atlas Cervical Cancer Cohort, or TCGA-CESC. This dataset provided molecular insight with the TSNE projections at the top left, showing clusterings of normal and abnormal cases. This genomic data that correlates with lesion severity with a huge variety of samples offered genomic data that correlated with lesion severity. I was able to extract over 1,056 features, normalize them using log transformations, and use them to identify early markers, which complemented the Harlem dataset data. The correlation heat map reveals some strong relationships among MRR21 features, with red being positive correlations and blue being negative correlations. To further validate my findings, I incorporated the GSE 178629 dataset from another genomic repository. This also offered over 1,000 samples focusing on miRNA21 and other related biomarker data, with its TSNE projections showing clear separation. The heat map indicated correlations among MRR21 variants, while top features emphasized MIR21 as being important. Once again, I processed these features, applied log2 transformations to normalize the dataset for consistency. This, together with the TCGA-CESC dataset, strengthened the model's ability to detect molecular signatures, enhancing the overall accuracy. On to the next part. The core technical innovation of this project was the mid-level fusion architecture. So here's exactly how it worked. I didn't just throw all the data into one huge model. Instead, I used a CNN, or a convolutional neural network, designed to analyze the pap smear images, extract all the complex patterns and features that are hard for the human eye to see. And then I also used a multi-layer perceptron to process the tabular data, the biomarker levels, and clinical information. Each network produced a compact 1 128 dimensional summary or embedding of its respective data. And then at this point, after each modality had been processed, I fused the data by concatenating these two embeddings. So this combined vector is then passed to a final classification layer with threshold optimization to make a diagnosis. To ensure that my results were both robust and reliable, I employed a rigorous bifold cross-validation strategy with batch sizes optimized for memory to once again make sure that this was able to be used in resource low settings. This means that I split my entire data set into 5 parts. I trained the model with an atom optimizer with a 1E4 rate 5 separate times, and each time I used 4 parts for training while holding out a different 5th part for testing. This ensured that every data point got used for testing at least once, giving us a true measure of how the model would perform on unseen data. I also utilized early stopping on the 20 epochs to prevent the model from overfitting and simply just memorizing the training data it was being fed. On to the results. So the training plots showed steady loss decrease for GS for both data sets, with validation stabilizing at around 0.15. And even though there was some slight overfitting with the TCGAC SC training, these results were able to indicate some pretty high convergence. The curves validated the model's learning efficiency across the data sets. The performance is exceptionally strong and consistent across all the 5 validation folds, with my average AUC, or area under the curve, being 0.955, and the highest peaking score being 0.966 on fold 4. For context, an AUC of 1 is considered perfect. I'm pretty sure you know this, and 0.95 is considered, I would say, pretty good. This significantly outperforms some traditional pap smear sensitivity, and it's very competitive, I would say, with some modern benchmarks. The average F1 score, which balances precision and recall, was around 0.944. Okay, so let's get into fold 1. Fold 1, the UMAP plot separated normal and abnormal clusters pretty clearly, with some overlap on the edge cases, as you can see. And the SHAP plot highlighted the image features as playing a key role in this fold. The AUC curve peaked around 0.95, so some pretty strong performance. The loss curve trended downwards to a 0.18, indicating some pretty good training going on. And the ROC's broad curve high area confirms reliability. The calibration curve, even though it was pretty deviant, was something to keep in mind later to work on. Fold 2, the UMAP also showed some tighter clustering and more separation, and the SHAP plot once again emphasized the image features as being really important. 0.7, reflecting some efficient learning, while the ROC curve maintained its really broad area. The calibration curve showed some minor deviations at the beginning once again, suggesting that some consistent predictions were going on. On to fold 3. Once again, the UMAP revealed some overlap in edge cases, so this consistent pattern showing up in the folds was something for me to keep in mind later to work on, as it indicated some complexity in what we had going on. And the SHAP plot again prioritized the image features and MRR21. The AUC score dipped to 0.93 due to these overlaps in UMAP, but the loss curve still drops to a pretty decent number. The RC curve maintains its broad area, and while the calibration curve exhibited some misalignment, it was pretty on par with what we expected. And then on to fold 4. Here again, there is some overlap in these edge cases, so I did start to notice a pattern going on at this point. And the SHAP plot highlighted the image features once again. The AUC curve climbed to 0.96, the highest it had ever been, while the loss curve settled at around 2.15, showing some solid convergence going on. The ROC curve widened a little bit, and the calibration curve had some pretty major deviations from what I expected in this fold. And then fold 5, slight overfitting with the UMAP, but pretty well with the tight cluster texturing. The shot plot reinforced image features all throughout. The AUC held a score of 0.94, and the ROC curve maintained its pretty broad shape. The calibration curve showed some major drift, and this essentially rounded out our five-fold evaluations. So a critical part of my work was making sure this could be used in resource low settings. So that's why I introduced the fairness analysis. I stratified the results by age and simulated regions to ensure the models performed equitably across different demographic groups. The fairness analysis showed an average sensitivity of 0.797 across demographics, but specificity was especially low at 0.197 due to some data imbalances that I had. That this suggested a potential bias in my data set, likely due to the simulated clinical data that I had, which pushed the model to overpredict abnormalities. Addressing this issue is a very critical for equity in this project, but I would like to address that it is not a failure, but simply a vital finding. It highlighted the importance of auditing AI models for bias and underscores that my future work must focus on collecting more balanced real-world data to ensure equity. This work was conducted under some significant technical constraints. All model training and analysis was done on a standard laptop with an integrated Intel CPU, sorry. This lacked the power of dedicated truly deep learning hardware that I would have liked, leading to very long training times and limiting some of the complexities that I could have taken with this project. Furthermore, as I just mentioned previously, the use of simulated clinical data, while it was necessary, provided a limitation that I need to address with real patient data in the future. Cross-sectional data, limited temporal insights, and data site diversity could affect some generalizability. Also, both the data sets used were Western biased, potentially skewing the results, overfitting in smaller subgroups, and computational demands for training also posed some hurdles that I needed to overcome. So where do I go from here? My future directions are pretty clear. Validate with some real-world data from global partners to eliminate these biases and improve generalizability. Develop for deployment by optimizing the model to run on low-cost, low-power edge computing devices, making it truly usable in those areas without resources. Enhance interpretability by integrating more advanced explainability tools directly into a user-friendly interface for healthcare workers, and more specifically, especially important, include GPU optimization, model quantization to 50 MB for edge deployment, and adding more biomarkers to make sure this model was truly accurate. So my ultimate goal was to transition this technology from just a research project into a tangible tool that could help reduce global health disparity in cervical cancer screening. So in summary for this whole thing, multimodal deep learning offers a lifeline, I believe, for cervical cancer detection. And I've developed a multimodal AI model that integrates pap smear images, molecular biomarkers, and clinical data to achieve what I believe is a significant foundation for these early cervical cancer detection. This project showcases the power of data fusion and provides a pretty robust framework for building explainable and auditable AI diagnostic tools. And while there were definitely some challenges around fairness and computational limits, I believe this work provides a strong foundation for creating accessible, accurate, and equitable screening solutions that could save lives around the world. Thank you. This was a really impactful experience for me, as this was my really first significant research project I had done. And I had a really good mentor who was always there to give me advice and responded pretty quickly to me. This experience also really shaped in my mind exactly what I wanted to do in the future with AI. So I say this was pretty impactful for me. I mean, research does look good on college apps, I believe. But personally for me, research is just really fun. You get to learn more things as you read these papers, especially in literature review. And just knowing that you're impacting real people out there in the world and building to this bigger goal is truly what I'm looking for.